Good afternoon, everyone. Thank you for showing up for discussion one or discussion part two, week one. The first discussion was taken by Sisong, and we covered mathematical induction in that one and runtime analysis, like the omega notation, big O notation, and theta notation. So the stuff that will be, yeah. Uh, Actually, for this first week, so what happens is like you have two discussion sessions, but we generally cover the same content in both the sessions. But since this is week one, we also covered a little bit prerequisites that you need for this class. The stuff that you learned in CSC 21. So we covered that part in the first session today, and this will be more towards what you learned in your lectures. Okay. Any more question before we start? Okay, and by the way, these discussion sessions are going to be recorded, so you can watch the recordings later on, either on podcast.ucsc.edu or it's also visible in your Canvas. Okay. So, couple of logistics before we start. So we have in-person and remote office hours. The schedule can be seen on Canvas. Please feel free to attend these office hours to get help on your homework or lectures. We also have one-on-one with TAs and tutors. I guess the spreadsheet is already there on Piazza. Feel free to sign up. So we have a spreadsheet where you just have to like put your name, the slot that you would prefer, and the stuff that you want to cover. Okay, but one thing, you cannot request for stuff that we haven't covered yet. Okay, or the ongoing homework. We are not supposed to help you with that in the one-on-ones. Also, homework 1 is released, which is due 10th April, next week, Wednesday. And feel free to ask any question on Piazza. We'll try our best to answer the questions. And during this discussion session, please feel free to interrupt me anytime you think anything is not clear or you want me to repeat something. Okay? Yeah, let's start. So this is again the prerequisites, the runtime that we'll ask you to give for a given problem. We mostly focus on big O. That's the one that's most important in this class. So big O is basically a worst case runtime analysis. Okay, it's kind of an upper bound. Big omega is a lower bound or the best case runtime analysis. And big theta is kind of a tighter bound. It's average case or the average runtime analysis. Okay. We won't go too deep into this because it was already covered in the morning session. But the basic idea, the overview, I just told you about that here. And one of the main part of this class is different proving techniques that you will be using to solve your questions. So the first is direct proof. That means like you can give some logical reasoning and like provide a straightforward proof. Sounds easy, but it doesn't apply to all the problem sets because we will see problems that are very complicated and a direct proof is not always possible. So we have prove by contradiction. In this case, what we do is we assume, let's say we are trying to prove that something is true when something happens, okay? So what we will do is we assume the opposite is true, and then we will show the inconsistency in that, and we use contradiction in that cases, okay? Prove by contrapositive. So something like this. So let's say we are trying to prove that A implies B, okay? So contrapositive of this basically means that negation of B implies negation of A. Okay, these are one and the same thing. So sometimes it's easy to prove the contrapositive. So you can just change your statements and go with the other statement to prove. Prove by induction. So in induction, I think all of you are aware about it by now. We basically assume that whatever we have seen till now is true, and then we try to prove it for. So we assume that P of k is true, and then we try to prove that P of k plus 1 is also true. That is also very important. So please review these topics once again, and if you have any questions or anything like that, come to office hours or one-on-ones. And in strong induction, we prove that everything before K is true. So that's like a strong induction. In a induction, we just assume that P of K is true. But in strong induction, we assume that everything before P of everything, like all possible values of N before K, is true. Okay. So yeah. Uh, so we have two types of graphs in this course. One is directed graph. So in directed graph, when something is, let's say this edge is given to you as uv, this basically implies that there is an edge from u to v. Okay. So this is like an ordered pair in this case. But this is this. And in undirected graph, let's say if you have an edge uv, it will be equal to vu. So this just implies that there is a connection between u and v. So you can go from u to v, but you can also go from v to u in that case. Okay. But in directed graph, that cannot happen. You can only go in one single direction. Got it? Yeah. So there's one more a special kind of directed graph called DAG. That is directed acyclic graph. In that graph, you have basically cycles. Okay, something like this. So in this one, we can see that there is a cycle here. So this is a DAG. Okay. Like if you start from A, you can again come back to A. That means you found a cycle. So that is a DAG. Yeah. Oh, sorry. This is a direct cyclic graph. In acyclic, you do not have graphs. Yeah. Thanks for correcting. Yeah. So this is a cycle, but in a DAG, you won't have these things. You know, one of the edge will not be there. Sorry for the mistake there. Thank you for correcting that. Is it clear? Okay. So this is stuff that we have learned till now. We have seen explore algorithm in the second lecture, I guess. In that algorithm, we take G and S as your inputs, and then we run this explore. Basically, it returns all the vertices, a list of vertices that are reachable from S. I'm not sure if DFS is already covered. Is it covered? Okay, so we won't go too deep into this DFS yet. Okay, we will only stick to explore for now, and we will try to solve a problem using explore. Okay. Any question in this one, like how explore works, or like if you want me to remind you a little bit about that? Is it clear? Okay. So we will take a look at this problem now. So the problem statement, it goes like this. You are given a directed graph G where each vertex is labeled by either 0 or 1. And you have given two vertices, S and T. S is basically the starting vertex and T is the ending vertex. So you want to determine if there is a path in G that starts from S and it ends at T, and the vertices in that are a sequence of 0 and 1, alternating sequence of 0 and 1. Okay. So you want to find that. So what it basically means is, if you start from S, go to T, and let's say you have V1, V2, V3. So if this is 0, then this should be 1, 0, 1, and 0. The vertices in that should be like alternating sequences of 0 and 1. Okay. So you want to find if such a path exists in the graph. Any question? Is this problem statement clear? Yeah. So let's take an example. So in this graph, does a path exist from S to T with alternating vertices? It does? Yeah. And what will be that path? Yeah, exactly. S to A, S to A to B, and then B to T, right? it's 0 1 0 1, right? So indeed, so this one should return true to you. Okay. I hope like this cleared the problem statement a little bit. Okay. So what are the inputs in this problem? Like what is the input? Yeah. So whenever you have a question, try to identify the input set that you have and what it is trying to like generate or what it is asking you. So what is the input in this case? Yeah. Yeah. So let's say the graph itself and SNT, right? And what will be the output in this case? Yeah. It is either true or false, right? So exactly the input is basically the graph that is given to you. Each label is, each vertex is labeled by 0 or 1, and you have two special vertices S and T that you want to find a path between. Okay, and the output is simply true if there is a path from S to T with alternating labels. Otherwise, it should return false. Yep. So any ideas how you can solve this problem? Maybe take a little bit of time. Maybe take 1 or 2 minutes to discuss it with your partners, and then we will take it from there. Yeah. So, yep. For clarifications. No, that's just an example, completely different from what we have here. No, here, just an example. But what we're trying to do is we are trying to uh, see how to solve this problem in a general scenario. Not for this. Yeah, yeah. By the way, for this example, there is no path from S to T with alternating 0 and 1s. Okay, so any solutions? Yeah. Yeah, that's correct. For this specific example, there is no solution. So this one should return false. So what we are trying to do is we are trying to solve this problem statement for general case. So like we are trying to come up with an algorithm for the problem itself. Yeah. Oh, you can do that. Actually, we will come to that in a little bit. Yeah. Hmm. That sounds like a good algorithm. Anyone else? Yeah.
So you can do the normal exploring graph algorithm as we normally do. However, when you're talking about where exploring a node, you for however you're storing the explored nodes, you also include what was the previous binary digit,
Mm-hmm.
and what that will allow you to do basically is um, not only will allow you to traverse like in the normal explore algorithm, once you explore a node, you can't go back to it.
Right.
However, we have to, in this case, we have to make sure that we can go back to it if there's a different previous binary digit, if that makes sense.
That would make it exponential. The algorithm would be exponential because
No, because if you only have, there's only zeros and ones, right?
yeah.
So then you can only visit node twice, with the previous number being zero and previous being one.
Okay.
So, so just with that change to the graph, and just with that change to graph, also with whenever you're exploring a node, only consider the next node to be the ones with a different binary digit. And those two
Mm-hmm.
changes before.
Okay. So we got a couple of solutions for this, and you guys are thinking in the right direction. So the common solution that I saw is a modified version of explore, where if you start from a particular vertex, you only traverse to a next vertex if it is a different binary digit, right? So that's the common solution. And by the way, this type of solutions are called modification, where you are trying to modify a already given algorithm that you know. So in this case, specifically explore. So you already know how explore works, and you are trying to modify the explore itself to make it work for this problem statement. Okay. So we are way beyond this slide. So we already discussed about explore that you guys are trying to modify. So let's see how to proceed with that. So first thing first, you define your problem statement in a very clear way, okay? So that like think about your solution is being read by a different person, and if they read your problem, they should be able to implement it without any external information, okay? So what we are saying is like let's say we will run this alternating explore. It takes three inputs, G, L, and V. G is the graph itself. L is a function which basically tells you whether your vertex is 0 or 1. Okay? And you're also given V. That means the starting point or the point that you are at right now in that given instance. Okay? So what you do is you mark V as visited. So far it's almost similar to explore. Then for all unvisited neighbors of U, such that L of V is not equal to L of U, that because we need that alternating sequences. So that's why we check for this condition. And we only recurse on U which satisfy this exact condition. Okay. So in case of explore, we just recurse on all the possible neighbors, right, which are not visited. But in this case, along with that condition, we also need to check if their value is not same. Okay. And in the end, we check if T is visited. If it is visited, that means we have indeed found a path from S to T. Otherwise, no, right? So based on that, we return true or false. So now, so once you have the algorithm, the two things comes. The first one is if this algorithm is correct. Is this algorithm correct? Does anyone think that this algorithm doesn't work? Well, yeah.
I think so. I'm sorry. I'm gonna really quick try to like.
Yeah, exactly. So if you think this is wrong, then you have to come up with a counterexample. Yeah. Yeah. Cool. Do let me know if you are able to find it. But if it is true, then we'll have to like systematically prove that this algorithm is true. So how will we prove it? Any suggestions here? Yeah. Mm-hmm. Yeah. The exactly like how you did proof for your explore, right? Okay. So this is what we need to prove. So we need to prove that if V is visited, then there is a path from S to V. with alternating labels. Okay. So we are going to use a loop invariant proof for this one. So in this case, our loop invariant is, let's say after ith iteration, all the vertices v that are visited, there is a path from S to V with alternating sequence of 0 and 1. Okay. And the base case would be that you just start at S, right? Because S is visited and it's a very trivial base case. S to S, it is by default alternating sequence of 0 and 1. Okay. If it is 1, then 1 is fine. If it is 0, then it will stay 0. There won't be any case where you have 0, 0 or 1, 1. Okay. So the base case is covered. Now let's take a look at the inductive hypothesis. So we will prove that this loop invariant is true after k iterations. Okay. And then we want to show that after k plus 1 iteration, it is still true. So let's see that. So then there comes this induction step. So we are saying that the algorithm is returning, like working fine till kth iteration, right? So assume that this vertex u is visited on the k plus 1 iteration. Okay. So by this algorithm, this means that we must have gotten to u from one of its neighbors v, right? So let's say that this v was visited in kth iteration, and in the k plus 1 iteration, this u is visited. Okay. And we can only go to that particular u if the labels of u and v are different, right? That's how the algorithm is. That makes sense? So what happens here is that by inductive hypothesis, we know that there is a path from S to V with alternating zeros and ones. Okay, that's what you are taking for induction hypothesis. So now what you are doing is, since V and U they have alternating labels, that means there is a path from S to U with alternating zero and ones. Okay, and that's how we prove that even after k plus 1 iteration, we still have the property of 0 and 1 alternating sequences being satisfied. Is it clear? Yeah.
I really like the technique alternation because one idea I was thinking of was like just saying all the paths that lead from S to T, but that could grow way too big in some cases. So I was just wondering, is there like a way where like we have like a boolean flag, and like every time we're going for like a 0 or 1, we like do like an AND operation with it to make sure that like signs match or whatever?
You can do an operation, or you can just use simple if case, because if condition is a constant operation, so it's fine. If you just use a if case, or if you do some operation on that and check for that, so it's totally fine. Yeah, that's also fine. You just want your next vertex to be something that is not you. That means if you are 0, if v is 0, then you should be 1. Yeah. Yeah. So basically, yeah, true. Any other question? Anything that is not clear in this one, in this proof? Okay. So what do you think? Are we done with this proof? Is this enough? Why not? Yeah. I don't know. So what we proved right now is that if there is a path, then the algorithm will return true, right? So is that enough? Yeah. Exactly. Because like you can come up with some very fancy algorithm which always returns true. In that case, this statement will be true, but the algorithm is just some rubbish thing, right? So we need to cater to that too. So as he said, we need to prove that if there is no path from S to T with alternating sequences of 0 and 1, then we need to return false. Okay? Yeah, so this is another way of saying that. So if V is not visited when the algorithm terminates, then there is no path from S to V. So we are saying the same thing in a different words. Okay? Is that okay? Okay. So let's prove that. So when you're trying to like prove this kind of scenario, like where A implies B, So what we generally do is we assume that A is true, and then we make our case from there. Okay. So in this case, what we are saying is that if V is not visited, then there is no path from S to V. Okay. So in this specific example, we have proved it with contradiction. So what we are saying is that let's say there is a path from S to V, but the algorithm failed to find it. Okay. So let's say this path is this thing here in the bottom, S to V, and algorithm was successfully able to find all the vertices till this point U. But something happened and algorithm started giving you wrong output from that point onwards. And since this is the valid path, that means that L of U is not equal to L of W, right? For a valid path, that has to be true. And your algorithm should work here because when you are at this vertex V, you are recursing at all the points that has a value different from this particular U. So you should have been covering that vertex W. So that's why this is a contradiction. This is not consistent with what your algorithm is doing, right? So that's why by contradiction we are showing that if V is not visited, then there is no path from S to V. Is it clear? Any questions, clarifications needed? So let me summarize what we did. So first we showed that if V is visited when the algorithm terminates, then there is a path from S to V with alternating labels. And then we also showed that if V is not visited when the algorithm terminates, that means there is no path from S to V with alternating labels. Okay? So therefore T is visited if and only if. So that this is the key here. So T is visited if and only if there is a path from S to T with alternating labels. And by the way, this kind of proof is called bidirectional proof, where we are like, this is like a forward direction, this first one, and this is the backward direction. So I don't think you can come up with a counterexample for this one, because this is indeed true.
Yeah, what my issue was, I was thinking about if the edges had binary rather than the nodes.
Mm-hmm.
This was node, so that's what my.
Okay. But doesn't this feel like you are trying to reprove stuff that you already did in the class? Right? You did something similar to prove your explore algorithm, and this question, again, you are doing the same thing from scratch. This seems like too much work, right? Maybe we can like use that algorithm and solve this problem. So before that, let's do the runtime analysis. Same as your explore. It is the summation of 1 plus degree V for all the vertices. It comes out to be V plus E. I think this was covered in the class. So this is V and this is E. Okay. For directed graph, this is E. For undirected graph, it will be 2E. But big O is still the same. Okay. Any question in this one? Okay. Yeah, so exactly what I was saying, that modification algorithm can be a little bit messy because you need to prove it. And if your algorithm is not straightforward, like in this case, it was very easy, right? You go to the next vertex only if the label is different. But it can be like a lot of if-else cases, a lot of scenarios. In that case, your proof will become really tough to do, right? So what to do? So you can use the algorithm that we have already taught in class, and you modify your input in such a way that the algorithm fits in that one. And we can just use the correctness property for that given algorithm and somehow prove that solution. So for CSE 101, we highly recommend not to use modification algorithms, because if it isn't broken, then there is no need to fix it. Right? There's no need to like reinvent the wheel. So this takes us to this special or like the easy way of doing things using reductions. So what we'll do is we will modify input so that we can use an existing algorithm as a subroutine. So the keyword here is this thing, modifying the input and existing algorithm as a using existing algorithm as a subroutine. Okay. So what that basically means is, so this is the original problem wherein you have this input I and this output, and then you have this solution for problem A, which gives you the right output for a given input. And using reduction, what you do is you modify this input to this I prime using some function or some like modification technique or rules that you have come up with. And then you give this input to this green box that is basically a subroutine that you already know. Okay? And the output of this will be the actual answer. So in this case, you do not have to prove this thing because that's already proven to you. Is it clear? So can you think of a reduction based method that we can apply to this problem statement? The same problem that we were trying to solve earlier. Yeah. Oh, that's a good observation. Yeah. So let me create a new page here. So what you're basically saying is that if let's create a graph first. S to T or T came really soon. Let's have some other nodes in here. A, B, C, D. Now let's say this is T here. 0, 1, 0, 1, and then 1 and 0. So what you are saying basically is remove these vertices here, right? Or the edges, these things. Where you have like same labels for the vertices, you remove those edges. Yeah, because that thing will never be part of your solution, right? So yeah, indeed that is like a reduction based thing because we are modifying our graph from G to G prime. And in this G prime, we remove all the edges that have like same labeled nodes. Okay. Yeah. So this is step 1 that we just did. We described like how we are modifying the input, and then we will run some existing algorithm, and then we will check for this output from step 2 to return the appropriate value. So we created a graph G prime from G by removing all the edges UV such that L of V is equal to L of U. In step 2, we simply run explore from S, and in step 3, we check if this T is visited. If it's visited, then you return true, otherwise you return false. Is this algorithm clear to you? We still have a lot of work to do, like we need to prove it works correctly. But is this algorithm clear? Okay, so how will you prove this? So, so for solutions involving reduction, we want to show one-to-one correspondence from G to G prime. Okay. So here also we will use a very similar proving technique, but let's see how to do it. So yeah, so the first thing is like if your algorithm is yeah, so if you, when you run your algorithm and then you check that your T is visited, then you return true. So that's what you want to prove. Like if there is a path from S to T with alternating labels, then your algorithm should return true. So how will you prove this? So what are the assumptions in this case? Yeah. So the assumption is that there is a path from S to T, right, with alternating labels. And what are we trying to prove? That the algorithm is returning true in that case. So we will assume that this first half is true. That means there is indeed a path from S to T. And we will assume that this path is this thing here. S to V1, then V1 to V2, v2 to v3, so and so forth, and the last thing is vk to t. Okay, so let's say this is a path from s to t, and then we want to show that the algorithm will return true. Since this path is alternating labels, all the edges in this path will be retained in your graph G prime, right? Because in G prime, you're only removing stuff that has same labels, right? But for every edge here, for every edge uv, we know that L of u is not equal to L of v, right? Right? So nothing in this path is removed. So that means this path is already always going to be there in your G prime. So that's how this one-to-one correspondence is there. If there is a path in G, that means there is a path in G prime as well. So because of that, this thing is true. That if T is visited, then yeah, indeed there is a path from S to T. Are we done? Again, always ask this question: are we done, or do we need to do more? Yeah. And this is CSE 101, so the answer is always going to be no. So what do you need to prove? The same stuff that we did earlier, right? If there is no path, then the algorithm should return false. Uh, I don't know if an example is required, like why we need to do more. But in any case, like let's say that someone else, like somebody else comes up with a very different algorithm, and the algorithm it goes like this. You remove all the edges uv such that L of v is equal to L of u. Okay, exactly same as we did, but that person has added one more modification. They have added this edge directly from S to T in G prime, right? So in this case as well, if there is a path, the algorithm will return true. But the bad thing is this algorithm will always return true, right? Because there is always going to be a path from S to T because of that small modification there, right? So if we just stick to everything that we have done till now in terms of proving, then this algorithm will actually slip from our radar, right? It will give it to you that this solution is indeed correct, but it is not. So how do we catch these things? We want to prove that if there is no path from S to T with alternating labels, then the algorithm should return false, right? And that second thing, this algorithm will fail that, right? Because it is never returning false. It is always returning true to you. Okay, is that clear? So we already showed this, and now we want to show this thing. Does this remind you of anything, like from maybe from CSE 21? So the first statement says that if there is a path from S to T with all the properties satisfied, then the algorithm returns true. And the second thing says if there is no path from S to T with alternating labels, then the algorithm returns false. Do you know like what it is called? I think we just discussed in the previous problem. Like what kind of proof is this? Exactly. This is the same old bidirectional proof. Okay. So this is the forward direction, and this is the backward direction. And this thing here in the brackets is the contrapositive of the backward direction. Okay. And like just to give you a small example of like how to convert your statement to a contrapositive statement. So here what we are saying is like if true, this implies that there is a path, right? So the contrapositive of this would be if there is no path, implies it's return true. Oh, sorry, return false. Right? So it is nothing but this thing here. So these two statements, they are one and the same thing. Okay, so you can prove either of these. Sometimes like it is easy to prove like statement 1, sometimes it is easy to prove statement 2. So based on the question, you can just choose one. Is it clear, or do you need any clarification here? So again, if there is no path from S to T with alternating labels, then the algorithm returns false. So what is the assumption? Assumption is that there is no path, right? And what are we trying to prove? We are trying to prove that the algorithm will return false in this case. So let's see. So since there is no path, we can safely say that the alternate, so we can say that the vertex u and v, they do not alternate between 0 and 1. Or in other words, we can say that there exists at least one edge where these two labels or the two vertices are labeled by 1 or both the vertices are labeled by 0. Okay. So basically what that means is like from S to T, there will be at least one edge going from A to B where both A and B are 1 or both A and B are 0, right? That's why there is no path, right? And in G prime, all such edges are removed, right? So this thing will be removed from here. That means there is a discontinuity between S and T. They are no longer connected. So if you run your explorer from S, since that AB edge has been removed, you will never reach your T, right? So that's why in that case, the visited of T will be false. Does that make sense? Or there is one more case. In that case, there is no path from S to T in the first place. That thing will always return false to you, right? Is this clear? And I think this is very similar to the problem 4 that you have in homework 1. So here we have like vertices labeled 0 and 1. There you have 3 labels, 0, 1 and 2. Okay. So this problem will be a good starting point to solve that one. So yeah, so we proved both the statements and that's why the algorithm is correct. So what's the runtime? So what is the runtime to create your graph G prime? Yeah. What about vertices? You're also copying the vertices, right? But you are going to check all the vertices too, right? So it will be V plus E. What is the runtime for running explore on G prime? Yep. This is the bread and butter of this class. Explore, DFS, yeah. What is the runtime? Exactly, like what we did, like proved earlier. It is big O of V plus E. And what is the runtime to check if it is visited or not? It should be a constant operation, right? You already have your array visited, you just have to like plug in the value and check it out. So let's say this is a constant time. So when you add all of this stuff, it will be big O of V plus E. Right? A linear algorithm. Yeah. Yeah. So what we assume here is like when you are creating a new input, you are copying everything from the graph, and then you are removing stuff. So copying everything in your graph is basically a constant, a linear operation. You're copying all the vertices and all the edges. So that's why it's V plus E. And in a lot of cases, it will be this value itself, right? Because you are just removing stuff. So it is always bound by the actual graph. Yeah. Any other question? And you know, like what was the beauty of the reduction thing? We did not prove the explore. We just assumed that explore works perfectly fine, right? If there is a, we just showed like there is a correspondence from G to G prime. And if there is something in G, we show that it has to be in G prime. If it is absent in G, then it is absent in G prime as well. And the explorer will take care of the logical thing in there. Okay. So this marks the end of our lecture, I guess. Let's see if I have anything else. Okay. Any questions? We just finished. Okay, guys, thank you for showing up and good luck with your homework one.